So now we start our description of making nanostructures from the bottom up. And there are many approaches to doing this. We will begin with organic synthesis or simple chemistry or complex chemistry, making structures by putting together simpler structures in a fairly well-determined way. We'll then talk about self-assembly, in which weaker interactions, weaker than the covalent bonds that help hold chemically synthesized structures together, can draw molecules to interact with one another. So, for example, pushing oily molecules together in a watery solution. Vesicles are micelles, structures that comes from that type of self-assembly. And we'll talk a little bit about the thermodynamic aspects of self-assembly. We'll give an illustration of a self-assembled machine that resides inside the cell, the mitochondrion, based on this self-assembly of fatty molecules in the presence of water molecules. We'll then talk about techniques for making self-assembled molecular monolayers, and then a number of structures that are made by growing crystals, but doing it in such a way that the growth in one direction or several directions is retarded or accelerated by kinetic control of growth in particular directions. So this is for the growth of nanowires or quantum dots. We'll end with a great fun topic, DNA nanotechnology, a topic of great promise and certainly already producing some quite remarkable nanostructures very efficiently. Let's start with organic synthesis. Most chemists would claim that they, chemists, have been doing nanoscience for many years before the word was introduced into the language, and they're basically right. Some quite remarkable nanoscale structures are made by the pretty hard route of synthesizing them from the ground up. This structure over here is made from a dendrimer. That is a polymer that branches repeatedly to form this tree-like structure that gets ever denser as you go away from the center of the dendrimer. So you see here this thing now is sealed off, and this particular example here is in an application in which this dendrimer sphere has been used to trap highly reactive chemicals that would not otherwise survive without reacting with something. This light-to-charge converter is a molecule we will look at in detail in Chapter 8 when we talk about molecular electronics. This component here is a chromophore. It's a dye that absorbs light in the visible. When it absorbs light and becomes excited, the electron that is generated in the excited state transfers rapidly to this electron acceptor here. This molecule here fills the ground state with an electron rather rapidly, and the result is then a long-lived charge-separated state with a plus charge on this molecule and a minus charge on this that can be used to do chemical work. Down here is a molecule that its inventors called a nanomuscle. The reason for this is these rings here are free to slide on these chemical spindles, and this group in the middle has a charge that can be changed by the local chemical environment. So depending on the charge here, the rings can either be pulled towards the middle or pushed apart. And so if the rings have sticky legs on them, shown here, and the molecule sits on a surface, cycling the acidity of the environment can cause this thing to expand and contract and walk over the surface. So quite remarkable structures. How on earth does anyone make anything like this? The richness of organic chemistry is based on carbon hybridization. As you know, carbon has 2 electrons in the s orbital and 2 in the p orbitals. However, the s and p orbitals are close together in energy, and so these can hybridize then to form 4 orbitals composed of mixtures of s and p states, in which the vertices of the orbitals point towards the corners of a tetrahedron. This is the usual sp3 hybridization of carbon, and one sees it in diamond. In the middle, I show sp2 hybridization of carbon, and this is the more familiar form of carbon in graphite, which I'm illustrating here. And then finally, sp hybridization And the example at the top there is acetylene, where the carbon is triply bonded. Because of this ability to change its bonding into many forms, carbon can form some incredibly complex structures. In order to build structures up systematically, one needs to place on the starting molecules reactive groups. And reactive groups fall into two broad categories. Nucleophiles are portions of molecules that have occupied states that are very high in energy and therefore like to donate electrons. Conversely, electrophiles are segments of molecules that have unfilled states that are low in energy and like to take two electrons. And the usual results of these processes are to cause bonds to break and reform. There are reactions in which single electrons can be donated. These are called free radical reactions, but free radicals are unstable, and so they usually proceed to another step. Also in organic chemistry, many structures are ring structures. You saw me draw the structure of graphite, and so that adding or subtracting electrons at one point in the ring can cause electrons to transfer around the ring. And finally, we'll mention the fact that many of these reactions are coupled to groups that can donate or accept a proton. These are called acid-base reactions. Happily, as a budding experimental nanoscientist, you don't have to know all of this complexity. I'm showing you here a couple of off-the-shelf reagents. One is an NHS ester, the other a Mali imide, and they have the property that they will react rather specifically in fairly mild conditions with chosen groups. So in the top image, the R is anything, and it is coupled to an amine, and the NHS ester will react specifically with an amine to form the amide bond shown on the right of the slide. This chemistry is so robust that pretty much anyone can do it. If you order your favorite R2 in this slide coupled to an NHS ester, and you have an R1 of some sort with an amine on it, by following the manufacturer's instructions for the NHS ester, you can make the reaction go. Another widely used reaction is the reaction of a thiol with a Mali imide. And so the Mali imide is this group shown here. The reaction is a little more complex than this formation of an amide bond up here. It proceeds through an intermediate. But the net result now is that R1 is again coupled to R2 via this sulfur linkage. Another essential step in organic synthesis is making sure that your reactive groups are the only thing that is attacked on the molecule. So if a molecule happens to have more than one reactive group, an important step is to first couple a protective group onto it, and then carry out the chemistry in conditions that do not remove the protective group, and then after the coupling chemistry is completed with some other group on the molecule, removing the protective group. Boc T-butyl carbamate is one example.